Now, recognize here that there's one partial problem with what, or potential problem that Popper is saying, is that Popper is being very, very bold, aggressive, one might even say arrogant here. He's claiming to know scientists better than they know themselves. He's walking around telling scientists their business. And even though, like I said, a lot of scientists like Popper, I don't think scientists generally like being told by philosophers how to do their jobs. But that's precisely what Popper is telling them to do. He's saying, look, if you're doing science, you got to be doing what I'm talking about. If you're not doing what I'm talking about, you're not doing science. For example, if you think that science is inductive, you're just wrong. What you're doing is either not inductive, it's either deductive, or it's not science. I can imagine Popper walking up to a practicing scientist and the scientist saying, look, I use induction all the time, and him saying, I'm sorry, you don't. Or at least if you do, what you're doing isn't science, because that's simply not how science works. And that scientist coming back at Popper is saying, who the hell are you to tell me what is and isn't science? I'm the practicing scientist here. I'm the one who has the degree. I'm the one who has the job. If anyone knows what scientists do, surely it's scientists, not philosophers. Now, to be fair, this particular problem is not unique to Popper. Pretty much any philosopher of science who claims that this is the nature of science is going to be running into this problem. Maybe it's not necessarily such a terrible objection. Oftentimes people can be sort of mistaken about what they do. This is actually one of the legitimate insights that Freud had. We can sometimes delude ourselves into thinking we're doing one thing when in fact we're doing something else. So this perhaps isn't necessarily the biggest problem for Popper's thinking. But it is worth recognizing that Popper is making here an aggressive, even potentially arrogant claim. The idea that throwing out the inductive method entirely, which is for many scientists what makes science science, is something that's arguably very unthinkable. It would be potentially a very bad idea. If a scientist wanted to push that, Popper is just going to fall back on Hume here and say, look, if you want to base science on induction, then you need to come up with a clear solution to Hume's problem of induction. And people have been trying to do that for 250 years, and there really is no consensus as to what the way of solving the problem of induction. So you really want to go into that sort of thorny rosebush there? Isn't it easier to just avoid the problem entirely and instead base science on deduction, on conjecture and refutation? So, whereas Hume believed that our beliefs lack a rational basis, our beliefs about the future at least, Popper is going to sort of split hairs on this. He's going to say, well, if by belief Hume means some sort of dogmatic assurance, a 100% certainty that we are right, then, yeah, Hume is correct. Anyone who claims with 100% certainty that they know what's going to happen tomorrow, that they know the way the universe works, that they know the laws of nature, anyone who makes that kind of claim, Popper is going to side with Hume completely. He's going to say, no, you don't. You might think you know it, but you do not actually know it. You cannot actually know it, because that's simply not possible to get that kind of information. But Popper thinks, look, we should change our understanding of what we mean by belief, because that rigid definition of belief, which is an idea which goes back at least as far as Plato, that idea that belief, in order to say that you believe something, to have a justified belief, you have to be certain, that's probably too strict. It doesn't seem like people typically mean that when they talk about beliefs. Beliefs instead should be something more provisional. Belief should be something like a tentative acceptance of an idea. An idea that, hey, here's an idea that seems to have worked so far. Maybe it's right, maybe it's wrong, I don't know, but thus far it's worked out more or less. And you combine that tentative acceptance with a clear fallibilism, a willingness to admit that you might be wrong. So even something like evolution, which a lot of people can get defensive about, we need to say, look, we have to admit that evolution might be wrong. It might be the case that tomorrow we'll find fossilized rabbits in pre-Cambrian strata, in which case we're going to throw evolution out. We shouldn't get defensive about that. We shouldn't take that personally. We should accept that as good scientific open-mindedness. So we take that fallibilism, that willingness to revise our ideas when they're necessary, and if that's what we mean by belief, this tentative acceptance with fallibilism and willingness to revise our ideas, then Popper thinks Hume is wrong. If that's what you mean by belief, that can very clearly be rationally justified. We do our best to find knowledge, acknowledging that the world is inherently uncertain, that our sense perceptions are imperfect. We can never see the world the way it really is. But that doesn't mean that we can't take this method of trial and error, this conjecture refutation model of science, and say that this is rational precisely because it has these qualities, this fallibilism, this open-mindedness, and this willingness to revise our ideas. That is what makes science rational, that open-mindedness. And it's also what makes it very, very powerful and very, very appealing to a lot of people. So I hope you can see now how Popper is going to really basically dissolve the problem of induction, at least as far as science goes. Because we never actually inductively infer theory from evidence. Rather, we hypothesize a theory, and where the theory comes from is, it can be a variety of different places. It can be something even as simple as a dream. I think that the structure for the benzene molecule arose because the scientist in question actually had a dream of a snake eating its tail. That's clearly not good empiricism right there. That's a dream. As I recall, either Watson or Crick, I can't remember which one. One of them got the inspiration for the double helix model in part because they had been tripping on acid. Hypotheses come from all sorts of places, and it's oftentimes they are divorced from evidence in any straightforward way. And then it's after the hypotheses are put in place that we then test that hypothesis against the evidence by trying to falsify it. So this means that we can never prove a theory, a scientific theory, is true in the way that we prove, say, a mathematical theorem is true. All we can do is fail to falsify a theory. And the more times we try to falsify a theory and fail, the more attempts that we make to falsify the theory, and the longer the theory survives those attempts at falsification, the more confident we can become. Popper's actual word, he says, such theories have greater degrees of verisimilitude. He doesn't want to call them true, because that implies that they've been proven in his mind. So he just says they have greater verisimilitude, which basically seems like another way of saying that they're true, which is a point I'm going to return to in just a second here. But again, the key thing for Popper's point is to recognize that falsification is purely deductive in nature. You start off with this hypothesis, you try to falsify it. If you succeed in falsifying it, then you've deductively falsified it. If you fail to falsify it, then it's deductively still open-ended. If that's how science works, then the problem of induction never even arises in the first place. Shifting onto objections now. Imagine that the Union of Associated Astrologers reads Popper's paper, and they recognize, you know what, Popper's right. We're not being very scientific. We need to get out there and make specific, falsifiable predictions. And that tomorrow, when you open up the paper and you read the astrology page, there's no, you will meet a tall, dark stranger, you will go on an adventure stuff. No, they make very specific things. You will find a $20 bill today on your way home from work. Well, okay, that seems like a pretty straightforward, very specific, very risky, very falsifiable prediction. Okay, so you go to work, you come home, and you don't find a $20 bill. And it's not just your horoscope that turns out to be false. Every single horoscope turns out to be false. All of them. You'd think even just that some of them would get it right by chance, but no, let's just say that even by chance they all fail. Those predictions that they make are invariably wrong. They never even get a single one of them right after a year of this new scientific Popperian astrology. Now, it seems like the astrologers could say, hey, look, our theories are falsifiable. I mean, they may be false, but at least they're scientific. Our theories qualify as science now. You have to treat our ideas as scientific because they are falsifiable. Frankly, that seems kind of ridiculous. I don't think that anyone, even Popper, would want to say that now astrologers are being scientific. And what that implies is that falsifiability is, at best, a necessary condition, but it is not a sufficient condition for a theory's being scientific. There's got to be something else on top of being falsifiable to genuinely qualify as science. And Popper doesn't really tell us what that is. I mean, this particular example seems to illustrate, well, it's not enough to be falsifiable. You also have to at least survive attempted falsifications once in a while. That might be a way to solve this particular example, but I hope you can also see how we could start poking at the edges and trying to find out, well, is that going to be sufficient? What exactly is the necessary and sufficient conditions, according to Popper, for something that makes something scientific? It seems like falsification is necessary, but it's not clearly sufficient. Okay, a little bit more biting of a problem here. Imagine that we perform an experiment in a lab. We're testing the idea that copper conducts electricity. That's our theory. We're trying to falsify it. We connect our piece of copper to the appropriate electrodes. We turn on the power, and no current passes through that piece of copper. Have we just falsified the theory that copper conducts electricity? We've performed an experiment, and that experiment has turned out not the way we expected. Can we now publish our paper and say that we've overturned one of the long-standing ideas in physics? No, it seems pretty clearly we have not just falsified that idea. What we're immediately going to conclude is that we screwed up somewhere. We miscalibrated an instrument, or we contaminated a sample, or we didn't connect the electrodes properly. Whatever it is, that's going to be the obvious conclusion we're going to jump to, and we're going to go back and 99.9999 times out of 10,000 we're going to find our mistake, we're going to fix it, and then we're going to see that everything works precisely as expected. Now, again, That's obvious for science. Every single working scientist has had an experience like that. They have them all the time. What we saw in the previous lecture, the bit about holism about testing from Willard Van Orman Quine, one of the consequences of holism about testing is a famous phrase which comes from the philosopher of science Thomas Kuhn, who we will be taking a closer look at later on. Kuhn says anomalies are not counterexamples because we often screw up, because human beings because scientists are human beings and human beings are imperfect. They construct their experiments very carefully, but no matter how carefully they are, there's always going to be a little bit of wiggle room, a little bit of margin of error. So if we insist on the idea that that anomalies are counterexamples, then every single theory in the history of science has been falsified. Not a single one of them would survive today. And so this brings me back to this quote that I opened up at the beginning with from Feynman. If it disagrees with experiment, it's wrong. And that simple statement is the key to science, Feynman says. It doesn't make a difference how beautiful your guess is. It doesn't make any difference how smart you are, who makes the guess, or what his name is. If it disagrees with experiment, it's wrong. That's Feynman's thing. Now, again, I trust Feynman actually understood that it's not that simple, but a lot of people who listen to Feynman do not recognize it's not that simple. It's not true that if it disagrees with experiment, it's wrong. You need to articulate this a lot more. It's if it agrees with well-structured experiments, repeated experiments, confirmed experiments repeated by different people in different labs. It's only after that very, very, very long process that you're going to go to the conclusion to say, now it's wrong. Science is as simple as saying if it disagrees with experiment, it's wrong, we've just destroyed science, because there isn't a single theory in the history of science that has not encountered a disagreement with an actual experiment, even like a well-structured experiment, because, and I'm going to repeat this again, anomalies are not counterexamples. But the problem then arises, how do we distinguish anomalies from counterexamples? How do we know when a theory has disagreed with experiment enough for us to say it's wrong? And how do we know when, okay, we've probably just made a mistake here, where we miscalibrated our instruments, we used a contaminated sample? Popper does not give us any answer to this at all. This is going to be a point that Thomas Kuhn is going to try to answer deliberately, and we'll see his attempt to answer this later on in a further lecture. This does seem like a very serious problem for Popper, because he wanted science to work deductively, cut and dry, clear away, and we're starting to see that science in practice does not appear to be that cut and dry. It's a lot messier. Okay, another objection here. The problem with the way Popper structures science is that, again, it is deductive, and deduction is always black and white. But science isn't always black and white. Science is often full of shades of gray. So consider a statement, this is a fair coin. That sounds like it should be a falsifiable claim. That should be a scientifically testable claim. So how could we go about falsifying the claim this is a fair coin? Well, if we had some laser measurements and stuff like that, some high-tech equipment, we could probably do the precise measurements necessary to see whether or not it's a fair coin. But let's assume we didn't have that kind of data, that kind of refined instrumentation. It seems like one way to falsify this claim would be to flip it 100 times and see what happens. Record it and see whether or not it looks like it's coming up with at least roughly a 50-50 distribution. Let's say that we do that. We flip it 100 times, and it comes up heads all 100 times. Can we now deductively conclude that it's not a fair coin? Can we say that we have deductively falsified the claim that it is a fair coin? And hopefully you know enough about statistics to know that no, you can't do that. Not deductively. I mean, inductively, again, it seems less plausible. It seems to strain credibility that this thing is still a fair coin. But deductively, you can't get there, because even fair coins will have long stretches of order. You will get, on occasion, very rare occasion, but on occasion, 100 heads in a row. So the statement, this is a fair coin, is logically compatible, deductively compatible, that is, with all possible outcomes. You can flip a coin 1,000 times, 100,000 times, 1 billion times, get heads every single time. You cannot deductively conclude that it's not a fair coin, because any possible series of outcomes is still statistically possible, granted unlikely. So it seems that that statement, this is a fair coin, is unfalsifiable and hence cannot be tested scientifically. But this isn't just a problem for flipping coins. This is a problem for any field that wants to use statistics, any field that wants to appeal to probabilities in making their scientific claims. Now, you don't have to have a whole lot of experience with science to know that the statistics and probabilities are at the heart of most sciences today. I mean, quantum mechanics is almost entirely about probabilistic systems. It's not just quantum mechanics or physics. Population genetics relies crucially on statistics. Social psychology, economics, all of these things use probabilities. They use statistics. If Popper is right, then none of these things qualify as actual sciences because none of these things are deductively falsifiable. And that's a major, major problem for Popper. At the very least, we're not going to be able to dodge the problem of induction by saying that science is based on a deductive logic. Because if that's the case, we're going to end up throwing out probably 95% of things that most people think qualify as science, because that's how heavily science nowadays relies on probabilities and statistics. So that's a real problem for Popper's sort of cut and dry solution to the problem of demarcation. All right, another objection. We'll call this one the confidence problem. Let's say that we have a theory, then we try to falsify it 100 times in novel different ways with different people coming at it from different critical fashions, and every single attempt to falsify it fails. Now, the intuitive thing to say at this point is that this theory, which has survived so many attempts at falsification, is more likely to be true. Especially in contrast to like a theory that's never been tested at all. So we got two theories. One's never been tested. One has been tested 100 times and survived every time. Which one's more likely to be true? The common sense answer is the one that has survived testing. But the idea of more likely, that's inductive thinking. And inductive thinking was precisely what Popper wants to not rely upon. We can put this into practice. Imagine that we're trying to build a bridge. And we've got two techniques we could use to build it. One that's been used to build 100 other bridges, and all those bridges are still standing, even through hurricanes and earthquakes and stuff like that. And another technique which has never been tried before, never been tested. According to Popper, we have no scientific reason to prefer the first technique over the second technique. We might have other reasons. Maybe one technique is cheaper than the other, so it might be more cost-effective, something like that. We might prefer it on that basis. But we cannot prefer it on the basis that one is more scientific. Because according to Popper, you don't get more likely to be true. You don't get more scientific. All you get is falsifiable and unfalsifiable, black and white. Either your theory is falsified or it's not falsified. A theory that's been tested 100 times and not falsified is just as non-falsified as a theory that's never been tested at all. And this just flies in the face of common sense. But nothing Popper supplies gives us the equipment that we need to be able to say that we can prefer this theory on scientific grounds. It really does seem like we want to say that the first technique is going to be more scientifically trustworthy than the other. But Popper does not allow us to say that. Okay, another pair of objections going on here. This is a pair that comes from the history of science and from the SETI program, the Search for Extraterrestrial Intelligence. Some ideas in the history of science might have been falsifiable at one point, but don't appear to be falsifiable anymore. So consider the claim that the sun is larger than the Earth. This is something which is sort of obvious today. We know this to be a fact today. But there was a point in time in which we didn't know this to be a fact, in which this was a conjecture. It took a lot of hard scientific work to get to the point where we felt that the sun is indeed larger than the Earth. Or consider the claim that the heart circulates blood. That was a huge controversy for a long time over what blood was, what it did, or what the heart did. That's one of these ideas that baffled brilliant minds for a very long time. And eventually we figured it out. And now, of course, we have a very thorough theory of circulation and how that works. It doesn't seem like either of these ideas are falsifiable anymore. I mean, what possible experiences could we have? What possible experiments could we conduct that would prove that the sun is actually smaller than the Earth? How could we prove that? How could we prove that actually the heart doesn't circulate blood? These claims don't appear to be falsifiable, and that seems to suggest that they're no longer scientific. Worse, it might even suggest that they're pseudoscientific, but both of these seem like perfectly straightforward scientific claims. The sun is larger than the Earth, and the heart circulates blood. Haven't somehow graduated on to non-scientific status just because they're confirmed to the point where they're no longer falsifiable. I mean, I suppose maybe if it turns out that we're plugged into the Matrix or something like that, and in the real world the sun is actually smaller than the Earth, maybe that's how you could falsify it. But that seems to be really stretching the idea of falsifiability well beyond what actual scientists are going to want to use. So those kinds of historical claims have sort of a limbo status for Popper, and it's not clear that most scientists, most people for that matter, are going to be comfortable putting them in that limbo state. Next up, consider a claim: we are not alone in the universe. Is that claim scientific? Is it something that's scientifically testable? Well, it does seem like it's scientifically testable if it's true. I mean, if indeed we travel far enough from the stars and we meet, I don't know, Vulcans or something like that on another planet, well, then we will have proven the claim we are not alone in the universe, and it seems like we've done it scientifically. So that does appear to suggest that some things in science are indeed provable, absolutely. But notice what happens. What if it's false? What if we are the only intelligent life in the universe, or for that matter, the only life in the universe? Well, if that's the case, then it doesn't seem like there's any way we could prove the claim we are not alone in the universe false, just because the universe is too damn big. I mean, you know, the scope and the scale of the universe is so gigantic. Human beings are never going to be able to test every single corner of the universe. There will always be parts of the universe we haven't looked at. So it's going to be impossible for us to ever completely, 100% with certainty, say that we've exhausted the possibility that there's intelligent life in the universe, and therefore we have falsified the claim that we are not alone in the universe. So a statement like this seems legitimately scientific, but it only seems like it can be proven true. It does not seem like it can be proven false, and that's a problem for Popper's way of thinking about the nature of science. Okay, in conclusion, wrapping up now, I want to say two things. I want to say, first off, what Popper seems to have gotten right, and second, what Popper seems to have gotten wrong. What he seems to have gotten right is the idea that scientific theories have to expose themselves to the world. They have to take their ideas and hold them up against the world in a way that makes it possible to show that there's problems with those ideas. If a theory is immune to new data, if no data can ever change our thinking on a topic, then that theory is not scientific. He also seems to be right that scientific theories have to be risky, at least if they're on the cutting edge, at least if there's any amount of controversy around them. You have to make predictions that very well may turn out to be false. If you're not making risky predictions, then what you're doing is just sort of, you're playing it too safe to be legitimately scientific. Now, again, Popper was very keen to recognize that lots of theories appear to expose themselves to the data and appear to respond to new data, but don't actually do so. Again, Marxism and Freudianism are the standard examples here. They appear to take in new data and respond accordingly, but in fact, they really don't. All they do is try to preserve the theory. They never try to amend the theory or reject the theory on the basis of new data. And those ideas should not be treated with the appellation science. We reserve the appellation science for things that meet a higher standard than that. But Popper isn't completely right about everything. Popper also seems to have gotten some things wrong. Very few ideas in science are straightforwardly falsifiable in the deductive way that Popper wanted them to be. I mean, again, go back to J.B.S. Haldane's suggestion, a fossilized rabbit in pre-Cambrian strata. Even if we did find one of those and recognize it wasn't a hoax or anything like that, that actually would not falsify all of evolution. I mean, at best, it will falsify large parts of evolutionary theory, possibly common descent, age of the Earth, something like that. But it's not going to falsify other aspects of the theory. It's not going to falsify various genetic aspects of evolution, which we have confirmed experimentally in the lab on completely different bases than the kind of basis that we see with the geologic column. So even something like evolution isn't really straightforwardly falsifiable. Again, that's not to say it's not falsifiable at all. It's just not falsifiable in the deductive manner that Popper wanted it to be. It seems that Popper was likely sort of naive to think that all statements or all theories, all ideas can be sort of neatly divided into two clear-cut categories. One is being science and the other being non-science. Some things might fall neatly into these two categories, but the world which we live in is a messy place. Maybe we shouldn't expect it to be quite so black and white. Maybe some ideas can be more or less scientific than others. Sort of a scientific gray area, if you will. I mean, it doesn't seem impossible to suggest that you could come up with versions of Freudianism or Marxism that are more scientific than the versions put forward by their original progenitors. You could create ideas which are testable and potentially falsifiable, but are done so in a way that's are going to be not straightforwardly so, and if so, then it might not be on any worse footing vis-a-vis falsification than something like evolution. So in recognizing how the world can be kind of messy in this way, it does seem to suggest that a straightforward demarcation between science and pseudoscience is probably not terribly likely to be had. That's not to say that we can't make general demarcations. It's just not going to be as cut and dry as Popper wanted it to be.